So, friends and their students, what we have discussed is the problem of hydrogen atom, and what we have done is we have subjected Schrodinger's wave equation to the hydrogen atom, and and translated the Cartesian coordinates into polar coordinates, and then using variable separable approach, the three independent equations that we developed. And this is the set of these three equations. And it's rightly said that you have dealt with three dimensions, or theta and phi, and we have a set of three quantum numbers associated with the solution of the problem of hydrogen atom. Now, to be concise, to be precise, and not to complicate the things, we can see out of these three equations that this equation in terms of azimuthal angle is the simplest, and 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 the solution of this differential equation can be written. So, what we'll be discussing is quantum numbers. So we have this differential equation, and we can write down its solution, and we can write down its solution as phi of phi is a e to the power of iota ml times phi plus 2 pi. And we can see that the condition that the wave function obeys, and hence phi, which is a component of complete wave function psi, must obey is it must obey the same set of conditions that are obeyed by the wave function psi. Now, now to move on from here, what we have introduced is in the solution is phi plus 2 pi, and if I draw a small geometry over here, rightly remembering what we have is this is phi. This is the azimuthal angle, and if we seek a plane, okay, if we seek a plane like this, and this is the original position vector, this is our plane, and if we rotate it by 2 pi, we'll be back to the original state. So it's clear that phi and phi plus 2 pi both identify the same meridian of the plane. Hence, what is imperative here is that phi of phi can be chosen as phi of phi plus 2 pi, and the reasons I have already mentioned. And so to say that phi that we have originally for the differential equation, let's assume that is e to the power of iota ml times phi. Okay, so to say that if we compare these two equations, and this will be the solution that we choose for the differential equation in terms of azimuthal angle, and then we can see that this function is periodic, and we can have this a e to the power of I ml phi equal to a e to the power of I ml times phi plus 2 pi. So this thing can happen only when this ml that we have defined this ml is either 0 or it's a positive number or it's a negative number. So this ml is it is 0, including plus minus 1, plus minus 2, and so on and so forth. For hydrogen atom, we are talking about hydrogen atom. So 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 to say, if we go to the differential equation that we have here in terms of theta, this equation also provides a solution, and it provides a solution in terms of L, and that L is an integer, and this L can be equalized to ml, and we can have the values of ml that we have defined here. What will be ml will be, it is 0, plus minus 1, plus minus 2, and so on so forth to plus minus L. The L is basically the formal presentation of L comes as a solution to the angular part of the Schrodinger's wave equation. So here we have a wave function in terms of phi, here we have a wave function in terms of theta, and here we have a wave function in terms of r. So to speak here is that this L that we have that's introduced in the equation that I talked about, this constant L is basically known as orbital quantum number. And the solution of the third equation that we have here, this is the radial part of Schrodinger's wave equation for the hydrogen atom. And for this radial part that we have, capital R, as a wave function of the hydrogen atom, it also requires certain condition to be fulfilled, and this condition is that E that's involved in this equation, this E has to be positive, or have one of the negative values, like En, signifying that electron is bound to the atom. So the negative value that we have for this energy, when this equation is solved, that's purely a representation of the bound state, because electron is bound to the nucleus. So the energy that we have here, that we come up with this energy, this E, when this radial part of Schrodinger's wave equation is solved, this energy comes out to be minus me to the power of 4, then 32 pi square epsilon naught square h cross square times 1 by n square. And so to say, this can be treated as E1 by n square. Okay, this E1 can incorporate everything that we have left here, me to the power of 4 by 30 pi square epsilon naught square h cross square. And this n is an integral number, and its values can be 1, 2, 3, and so on and so forth. So what do we find from this equation is that this is precisely the same formula for hydrogen, for the energy levels of the hydrogen atom that we had discussed using Bohr's model. And this is the beauty of the Schrodinger's wave equation being applied on hydrogen atom, because we are naturally getting these numbers, these equations, and and we are not only getting the equation that's linked with the energy, we are getting the things that are not described purely in Bohr's model of hydrogen atom. Now, so to say, another important condition is coming in action here is that the equation that we have, the equation that we have in radial form, what is the condition here is that this n that we have, that we have this n, we call this as the principal quantum number. Now this n is called as principal quantum number, so to say. And this principal quantum number n, it can either be equal to or it has to be greater than that of L plus 1. And this L is already defined as the orbital quantum number, which comes as a constant for the solution of angular part of this Schrodinger's wave equation. So this requirement may be expressed as a condition on the orbital angular momentum. So you cannot have your orbital quantum number is having a restriction. So how can we write down that restriction? Is we can say that this L can have the values 0, 1, 2, so on and so forth, up to n minus 1. And so to speak, at this point of time, is that hence we are in a position to have three important quantum numbers that are spontaneously coming out of solving the Schrodinger's wave equation on hydrogen atom. And we come up with three quantum numbers here, and the first one is principal quantum number, and this principal quantum number is n, and this n can have the values 1, 2, 3, so on and so forth. And then we have orbital quantum number, and this orbital quantum number is symbolized as L, and this is 0, 1, 2, and so on and so forth, but it is restricted to n minus 1. And then we have magnetic quantum number, and we will try to analyze these quantum numbers separately, but here we are trying to have a closure of discussion on the problem of hydrogen atom. So we have magnetic quantum number, and this that's ml, and that can have values 0, plus minus 1, plus minus 2, and so on and so forth, plus minus L. So so if I have to write down the wave function now to exhibit the dependence of r, theta, and phi. I would like to write down this wave function as psi, in which I have r, and this r is a function of n, l, and then I have theta, and this theta is giving me l, m, l, and then finally I have phi, that is m, l. So this is the wave function. This is the wave function, wave function psi, that can be written in terms of r, theta, and phi for the hydrogen atom. And here we would like to stop, and then in the next level we will be talking about these quantum numbers in some detail.